Okay, everyone, let's get started. Any issues with the lab? Everyone finished with lab 3? Good. All right, we're going to assign lab 4 today. And but first I want to go through the exam real quick just to make sure everyone's okay with the material. Looks like the scores were pretty good though, so I'm just going to run through this pretty fast. If you have any questions, let me know. So the first question said, we gave a CPU design, assume the CPU has a bug where the wire labeled REG-CEL-EX could only be driven to the value of 1 in 2 bits. Which of the following instructions would still execute correctly? In this case, if REG-CEL was locked as 1, then the mux that controls what gets written back to the register file would only be forwarding data from input 1, which is the immediate field, right? So that would be this input, right? Instruction EX 31 down to 12. So the only instruction that would work would be the load upper immediate. Any questions? Okay, which RISC-V instruction will multiply the value stored in register 4 by 16? This would be multiplying by a power of 2 is shifting left, and in this case, the right format would be shift left logical x4, x4, 4. Sorry, shift left logical immediate x4, x4, 4, right? Because the value, we're shifting by an immediate value of 4 bits. This one sometimes trips me up because this is different than MIPS. In MIPS, it would have just, in MIPS, the shift left logical was assumed to have an immediate shift amount. And if you wanted a variable shift amount, you'd have to use the shift left logical variable instruction. But in RISC-V, they've changed it to where they added the SLLI. That makes sense? Everyone with me? Okay. Which code is equivalent to the code below? This is a concurrent assignment statement. It's assigning F, and it's using a nested ternary, statement. And this is checking to see if X is 0, 1, in which case it assigns F to 1, 0. If X is 1, 1, it's outputting 0, 0. If X is 1, 0, it's outputting 0, 1. And then the else case would be if F is what, 0, 0, right? In which case it outputs 1, 1. So it looks like it's just complementing X, right? Make sense, right? Well, the problem is that we don't have. Do we have a version do we have an answer here where we're complementing X? The first option is assigning F to be X NOR 1, 1. So if you do an X NOR with 1, 1.
That's the truth table for an X only though.
Right, it's the same, yeah, it's the same thing, right? So,
so why is it not number 2? XOR with 0, 0.
Well, so if you XOR with 0, 0, it doesn't complement. It'll just pass X through to F, right? If you did an XOR with 1, 1, then it would flip the bits of X. Does that make sense? So if you have, in other words, if your input, if X is 0, 0, and you're doing XOR 2 apostrophe B 0, 0, if you have a 0 XOR 0 is 0, right? And 0 XOR 1 is 1. So if you XOR with 0, 0, it's like an identity function. It just passes X through, right? If, on the other hand, you XOR'd with 1, 1, then it would complement, right? So in this case, we have 0, 0. This would be 1, 1. Does that make sense?
Yeah, that's exactly what it is. If we 0, 0,
One.
we get 1, 1.
Oh, right. Yeah, but that's an XNOR. So another option would be to do an XNOR, right? So if you have X NOR 1, 1, right? That should have the same effect, right? Does that make sense?
No, I'll talk to you about it.
Okay.
Because I did the truth table for an XOR with 0, 0, and I got the exact result.
Let's see. Maybe I.
We don't want to waste time.
Okay. Okay, so I think 1 is the right answer there. The option 3 is reversing the bits of X, right? It's reversing the position of the 2 bits of X. And option 4 is complementing X, but only if the inputs are 0, 0, and 1, 1. The 2 bits would have to be equivalent, right? Any other questions? David, does that make sense? Okay. Okay. When a program is being executed on the 3-stage RISC-V CPU, in which stage is the 6th instruction when the 3rd instruction is in WB? So if the 3rd instruction is in WB, the 4th instruction would be in execute, and the 5th instruction would be in fetch, meaning the 6th instruction would not have been fetched yet. So not yet fetched. This one says, assume the following Verilog module. Now this one had, this question, I didn't realize this until I was putting these slides together, but there was a small typo in here. So there were some extra backslashes in the code. No one brought this up. No one asked about this. The reason for that is because when I type up these questions, I put them in a text file in a format called GIFT, which is the format that Moodle uses. And you have to escape the curly braces in GIFT. So I had those escaped. And I think what happened here was, I don't remember exactly, but I think probably what happened was I imported the question as in the GIFT file, and then I went in and edited it in the web interface and pasted in the code. Probably I was messing with the formatting, and those backslashes got left in. So I apologize for that. So yeah, those red backslashes, I assume that everyone just ignored those because no one asked about it. So it says fill in the missing values from top to bottom for the test vectors for testing module AAA. So the idea is that C is 3 bits, and you form C by you duplicate A twice and concatenate B. So if A is 0 and B is 0, then the expected C should be 0, 0, 0. If it's 0, 1, then you should have 0, 0, 1. If it's 1, 0, it should be 1, 1, 0. And for 1, 1, it should be 1, 1, 1, right? So that should be the values in the 3rd column there. And then I have them encoded as, literals in decimal, right? Any questions? Okay. This one says, how many total bits comprise the inputs to module AAA? So we've got clock, reset, and 3 bits of init. So that would be 5 in total, right? And then we have consider the RISC-V microarchitecture shown below and assume the following instructions are in the corresponding pipeline stages. Which statement is true? So PC fetch contains the address of the instruction in decode EX. Well, that's not true because PC fetch would have the address of the instruction in fetch, right? Option 2 is ALU source EX is a don't care. So ALU source EX is going to be driven by the LUI, and the LUI instruction is not doing anything with the ALU, right? LUI doesn't use the ALU, so the ALU op is a don't care. Also, ALU source is a don't care, right? Actually, it's ALU source, is option 2 is referring to ALU source, but they're both don't cares, right? And so ALU op and ALU source are don't cares for ALUI. And then ALU op EX must be set to 1000. That's not true. And reg write EX is set to 0, which is also not true because the instruction in the write back stage is an XORI, which does write a register. So reg write EX, I'm sorry, the instruction EX is an LUI rather, and which also writes a register. So reg write EX should be set to 1. Okay, any questions? Okay, which of the following is a problem with the module below? Signal assignment statements have 4 bits on the left-hand side and 3 bits on the right-hand side. Is that true? So C is 4 bits, so that's the left-hand side, and A and B are 3 bits. So yeah, that's a problem. So that would be option 1 would be the answer there. It also has blocking assignments are improperly used within an always block. I mean, no, that's fine. In fact, you should use blocking assignments in an always block if the always block is describing combinational logic as it is here, not non-clocked. C is double driven. That's not true because C looks like it might be double driven, but because both assignments to C are in the same always block, it means it's not double driven, right? If you had an assignment of C outside that always block, then that would potentially double drive it. And the fourth option is there is no structural HDL in this module, which is not a problem. You don't have to always have structural HDL. Although in most cases, when you look at Verilog, it's very common to see structural HDL. But this one is purely behavioral. Okay, consider the RISC-V microarchitecture shown below. What is the value of the RDWB, reg cell WB, reg write EX? When the following instructions are in the corresponding pipeline stage as shown. So RDWB is going to correspond to the XOR I. So what is RD? RD is the register destination. So that would just be 3, right? Because you're writing to register 3. Reg cell WB should be 2, because the XOR is the results of the XOR are going to come out of the ALU and they're going to be passed into the input 2 on the reg select mux, right? And so, yeah, so because it's underscore WB, we're looking at this instruction. And so that should be a 2. And reg write EX is corresponding to the LUI, and that should be a 1, right? Okay. Which of the following system Verilog statements takes as input an unsigned 8-bit value and multiplies it by 3? This one would be, you're multiplying it by 3. 3 is not a power of 2. So how do you multiply by a non-power of 2? You have to add together shifted forms of A. So in this case, if you want to multiply by 3, you shift it by 1 bit to the left, which gives you the multiplied by 2 version, and then you add a shifted by 0 bits, right? Make sense? Okay. So that would be 3. Oh, and also the shift, notice too, this is a little confusing because I'm not actually using the shift operator. Instead of using the shift operator, I'm just shifting by adding zeros to the right-hand side, which shifts it to the left, right? Make sense? Okay, which of the following system Verilog statements will receive 3 1-bit inputs, A, B, and C, and produce a 1-bit output Y? That is true if exactly 2 of its inputs are true. There was a little typo in this one that said if at exactly. So the at was extraneous. If exactly 2 of its inputs are true. So this one, let's see, if A plus B plus C is 2, then exactly 2 of its inputs are true, right? So it would be option 3. Make sense? So option 1 is doing an XOR. So the option 1, if you do an XOR with A, B, and C, then you'll get a true output if an odd number of inputs are 1. The option 2 is you're ORing together A, B, and C, so that would be true if at least one of them was 1. One of the inputs was 1. Option 4 is basically the same as option 1. It's just written differently. And option 5 would be true if at least one input were 1, right? Or actually, if y was a 1 bit, y is 1 bit, right? Yeah, it says 1 bit output y. So actually, option 5, if 2 of the inputs were true, you'd probably get a 0 actually for y, right? Because you'd have a carry out of 1 that would get disregarded, right? So what that means is option 5 would be true if you had an odd number of 1 bits set. Okay. All right. Following system verilog code will generate a repeating sequence of n values in consecutive cycles. What is the value of n? Yeah, this one. This one's probably the hardest one on here. Anyone confused by this one? Yeah.
Afterwards.
This one you have to kind of work it out. So you start out with the state being, and so the state is 5 bits here, right? So it's 0. It's not working. 0, 0, 0, 1, 0, right? So we start out with a value of 2 and 5 bits. And then every clock, we're going to take bit 3 and bit 1, right? So this is 4, 3, 2, 1, 0, right? So bit 3 XOR bit 1, right? So 0 XOR 1 is a 1, right? And then you're going to concatenate that with the upper 4 bits of state, meaning that you take the upper 4 bits and you kind of just move them to the right by 1 bit, shift right by 1 bit. So you're going to have 0, 0, 0, 1. Make sense? Okay. Okay, so in the next cycle, it's going to be 0 XOR 0, which is 0, and then 1, 0, 0, 0. Okay, then 1 XOR 0 is 1, 0, 1, 0, 0. And then 0 XOR 0 is 0, 1, 0, 1, 0. Is repeating yet? No. 1 XOR 1 is 0, 0, 1, 0, 1. Then we have 0, 0, 0, 1, 0. Okay, it looks like we have our first duplicate there, right? So from this point forward, it's just going to proceed the way it did starting from 0, 0, 0, 1, 0, right? So it looks like this thing has a period of 1, 2, 3, 4, 5, 6, right? It's going to repeat the same 6 values. This, by the way, is called a linear feedback shift register. And this is one way to generate a pseudo-random sequence of values in hardware. The problem is that really, if this is 5 bits, ideally the period should be 32, right? If the period were 32, then we get 32 unique values out. That would be preferable, I think. But in this case, the generating polynomial is not a very good one, and we end up with a period of 6. You guys with me? There's other in fact, the original code that I came up with actually did have a period of 32, and I deliberately tried to make it have a relatively short period. Okay. Okay. What input value to the module below is a don't care? So this one assigns B as a function of A, but we're ignoring A bit 0 in there. We don't care about A bit 0, so A bit 0 is a don't care. And which of the following statements is true? A continuous assignment statement can infer memory. Not true. A continuous assignment statement is one that begins with assign. right? That cannot, as far as I know, unless there's something I don't know about, there's no way to get memory with an assign statement. An always statement is behavioral HDL. Yeah, yes, behavioral as opposed to structural, right? So yes, that's true. That's true. So that's the answer, right? If statements can be used outside of an always block, no. Signal can only be read by one always block within the same module. No, I don't know what that's all. I don't know what that's all about. That's not true. And always blocks cannot be used to design combinational logic. Not true, right? In fact, that's what the always underscore comb construct is for. So answer is 2. And then I think this last question, consider the following module. How many cycles of delay exist between signal A and signal B? So signal A goes through 1, 2, 3, 4 cycles of delay. And then there's that assign at the top, which assigns A delay 4 to B. But this assign is combinational logic, which means that A delay, there's no delay between A delay 4 and B, right? Those are going to change at the same time. There's no delay. So there should be 4 cycles here, right?
Yeah, I don't understand. I thought all 4 of those switch blocks were in parallel with the same clock, and they would all update at the same time.
They do, but inside that always, you only update these once, right? So you're going to update all these guys every cycle, and in fact, the way it's written, there's not even a data dependency here, right? Because notice I wrote these in reverse order. Now, even if I had reversed the order though, and like I set, A delay 4, and then I use A delay 4 in the next line, it still would have 4 cycles of delay, because these outputs are updated only after the always finishes execution, right? Because the always is generated as like an atomic block of code, right? So whatever's in A will be in A delay 1, and then whatever was in A delay 1 will move to A delay 2. This will create like a shift register, basically, right? And we can verify that pretty easily, I think, if we copy this and we go over here, and let's say I just create a file here called, what do I call it? What's it called? Foo or something? DDD, right? So we'll call ddd.sv, and I'll just paste it in there. Hopefully there's no Unicode characters. Looks good. And then vlog ddd.sv, and failed to open read ddd. Oh, because I'm in the wrong directory. That's why. Undefined. Ooh, okay. Well, there's actually, I didn't notice this. So there's actually an issue in the code. Notice that A delay 4 needs to be added to this list. No one noticed this either. A delay 4. Okay, so that needs to be declared. You can tell that this question was I'd modified another question to create this, and the previous version didn't have A delay 4 in it. That's why it wasn't declared. So let's try that again. Let's do another vlog. ddd.sv. Okay, now vsim. Actually, I don't need to vsim it. I already have QuestaSim open. I just have to find maximize. No, okay, I'll close that. Let's do vsim ddd. Okay, there it is. And okay, now we have A and B. We're not showing the other signals, so we need to re-simulate this with full design visibility. Okay, there we go. Now we've got our delays, and so we have to set up our clock. So I'll drag these guys in, force the clock. Sorry, not force, but force clock. We'll do the clock thing because I don't have a test bench for this. And then we'll force A to be, 1, and then run this. And you can see that, so let's see, let me try to put this in the right, let me move A down. Now let me move B down, right? Because B, okay, so you can see that B and delay 4 are just, equivalent, because those are, B is assigned to delay 4 with an assign statement. And then A is forced from the beginning. A delay 1, though, does not look like it's delayed, right? Why is that? Anyone know? Because there's a hidden clock edge there. So let me change A. So there's a rising, I think, clock edge there right at the beginning. That's kind of a, so let's change, let's just force A to be 0 now. And run it. Yeah, so now you can see the delay. So I'm changing, so this is one thing that's a little confusing because I'm changing A on the rising clock edge, right? The rising clock edge is when this always statement activates. So if I change A, which is the input to the always, at the same time as the clock edge, then what does the always statement see? Well, it sees the old version of A, right? So on this rising edge of the clock, it's still seeing A as 1, right? On this rising edge of the clock, it sees A as 0, even though it's been 0 for a whole clock cycle, and that's why you have that delay there. So A delay 1 is a 1-cycle delay from A, and then A delay 2 is another cycle delay, A delay 3 is another cycle, and A delay 4 is a 4th cycle. Make sense? Okay, sorry about the declaration issue, though. I did not notice that. Okay, and that was the last question. So any other questions? Okay. All right, so we've got Lab 4, and as I mentioned at the beginning of the semester, Lab 4 will be due at the end of the semester. So you have the rest of the semester. So it's due on December 6th. Okay, so reading day is December 7th, but that's a Saturday, so we have it due on December 6th, which is the last day of the semester. It's a Friday, December 6th. So you have like basically 4 weeks, right? And so you should have plenty of time. And actually, this one, it doesn't really require a whole lot of changes from Lab 3. The goal is to implement branch instructions, so we have to add support for that. Last time I talked about how, so RISC-V uses PC relative addressing for branches and jumps, unlike MIPS. If you remember from MIPS had a J-type instruction that had a pseudo direct address, whereas in RISC, all the jumps are PC relative, including jump register. Do I remember that right? Let's jump ahead to jump register. No, sorry, that's jump register is kind of a direct address though, right? Because direct jump register, you take the contents of the register and you add the immediate. So you don't add the program counter. But aside from jump register, jumps and branches are PC relative, which means that the immediate field in the branch or the jump, is added to the program counter. The problem is, what program counter are we talking about? Because we have different program counters corresponding to different instructions that are in the pipeline, right? So we have PC fetch, which is the program counter of the instruction being fetched, which is actually the instruction that appears in your code after the branch instruction, right? So in MIPS, they used to call this PC plus 4. They'd say, oh, branch targets are PC plus 4 plus offset. But in RISC, RISC-V, they changed it to be relative to the program counter of the actual branch instruction. So it's not PC plus 4 anymore. It's the address of the branch instruction itself plus the immediate, right? That's the target, right? Now you might say, who cares? Well, that does make a difference in how you calculate the branch target address. The way I always think of it is that in MIPS, if you wanted to branch to yourself, your branch offset would be -1. Right? So your branch offset of -1 would create a self loop. In RISC-V, the branch offset of 0 creates a self loop. And you can verify this very easily in MARS or RARS simply by having an instruction that like branch to foo, and then put foo : instead of in front of that branch. So that would create a self branch. And then you look at the offset. And so in RISC-V, the offset is 0. And in MIPS, it was -1, right? So just just keep that in mind. But I give you the code there to calculate the offset and the target address. And so I'm giving you that in 2 lines of code. You could combine this into 1 line of code. It would just be really long. So the challenge here with RISC-V is that the branch offset is taking bits from different places in the instruction. So you have to take instruction bit, and this is this is a B-type instruction, right? B-type, right? There's B-type and J-type. Yeah. So there's a B-type instruction. And so you take instruction bit 31, concatenate it with instruction bit 7, concatenate it with instruction bits 30 down to 25. And then, bits 11 down to 8. And then you have to add an extra 0, because even after you take all the bits that make up the immediate field in a B-type instruction and you rearrange them to actually get a number, that number is referring to a half-word address, a 16-bit address. So if you want it to be a byte address, you have to add an extra 0 at the end, right? Now, if you remember, MIPS used a word address for this, so you had to add 2 zeros. Okay, but then our fetch stage is word addressed, right? So when we calculate the branch target, we end up deleting 2 bits from the right. So I add a bit here and then I delete 2 bits here, which might seem redundant, right? But the reason I'm doing that is because I'm calculating the byte address here, because this statement is right from the RISC-V manual, right? The RISC-V manual tells you how to calculate the target, the offset for a B-type in terms of bytes, right? That's because everything is byte addressed, right? All instruction set architectures assume byte addressing. So if you read the RISC-V manual, you're going to get something that looks like this. But then for our processor, we essentially shift it 2 bits to the right, and divide it by 4 to get a word address. And then, of course, you have to add the program counter, right? And the program counter is PCEX. So this is the program counter for the execute stage, which refers to the address of the instruction in the execute stage, which you have to add that in your, right now in lab 3, you don't have a PCEX, you have a PC fetch. So you're going to have to add a delay. You have to delay PC fetch to become PCEX, right? That's just an extra register you have to add. Make sense? Okay, so now you have a branch address. What do you do with the branch address? Well, you're going to feed that into a MUX back to the fetch stage. So the fetch stage now has an option where it can fetch the next instruction, or it can fetch the branch target, or it can fetch the JAL target, or it can fetch the JALer target. And the reason why there's 3 different targets is because depending on the instruction, there's 3 different ways to calculate the target address, right? So for branches, I just described that. It's basically the program counter plus the offset. For jump and link instructions, it's a J-type format, which is, I have to look this up. Yeah, the J-type uses an immediate that you also add to the PC, but it's a longer immediate, and it's different scrambling, different bit order. Right? Makes sense? I don't know why they use this. I'm not sure why this was chosen, but it's just a strange bit order. You have to rearrange the bits, but I gave you the code for that here. And then for the jump register, this one's not PC relative. This one is basically just, you're taking the contents of the RS register and you're adding the sign extended immediate, and you use that as your effective address, your target address. Now notice that in this case, you're masking off the bit 0. Right? Why? Because that's what they tell us to do. That's how it's defined in the instruction set architecture. So the idea is that the register is assumed to have a byte address, right? And then they convert it to what are they doing? They're not converting it to a word address. They're masking off bit 0. So they're assuring that the register is divisible by 2, that it is a byte address, but that it falls on the half-word boundary. So that's what they're doing here by masking off bit 0, is that they're ensuring that whatever was in that register is aligned on the 16-bit boundary. Again, I don't know why, I don't know what the rationale for that is, but that's what you expect when you get the code from the assembler, right? So you have to make sure that you implement it that way in order to be consistent with the spec, the RISC-V spec. Okay? So what we end up with is these three different target options, as well as the just PC plus 1 option, right? Now the problem though is that you have this issue because by the time you even calculate those target addresses, it's too late. You've already fetched the next instruction in your code after the branch, the fall through instruction. You've already fetched it because it takes a whole cycle to calculate this target address, and at the same time you're already fetching the fall through instruction. So if you have a taken branch, or if you have a jump, which are unconditional. Jumps are unconditional. Branches are conditional, meaning that if you have a branch and you don't take it, then you just treat it like a no-op, right? But if you have a taken branch or a jump, you have to do something with that instruction that you've already fetched, right? Now there's 2 options. Option 1 is you can just always execute it, meaning that whatever instruction appears in your code immediately after any branch or jump is going to be assumed to be executed regardless of the outcome of the branch. That's called a branch delay slot, right? Early MIPS processors used branch delay slots. So how does that work? Well, you have to have cooperation from the compiler if you're going to do that, because the compiler is going to have to understand that there's the semantics of the assembly code is that whatever you put right after a branch is always going to be executed. So the compiler has to plan for that, right? And if there's nothing to put in that slot, then you just put a no-op in there, right? Which actually makes a lot of sense, because if you don't have a branch delay slot, then you end up having to put a no-op in there dynamically at runtime anyway, which is what we're doing here, right? So in our CPU, we don't have a branch delay slot, but if you have a branch that's taken, you have to essentially use the hardware to slip in a no-op, right? Now, how do you do that? how do you do that? You can't really do that because by the time you do that, again, you've already fetched the next instruction, right? You're fetching instructions from a synchronous memory. So there's no time to slip in a no-op because a synchronous memory takes a whole cycle to read, right? So we struggled with this for a while in this class, trying to figure out how to get around this. And the solution we came up with is that allow the next instruction to be fetched, but have a bit that will cancel it. We call that bit the stall signal. So what happens is that the control unit will put a stall fetch signal out, which means this is a stall corresponding to whatever instructions in fetch. Okay, then you put that into a delay register, and the output of the delay register is called stall EX. So the stall EX is whatever the stall fetch was in the previous cycle, which means that the control unit, when it sees stall EX, that is a reminder to itself that it wanted to stall the next instruction, right? And so it basically uses that stall EX to disregard whatever instruction is being executed. You guys with me? So in other words, it's like a note to self. It's saying, the control unit is sequential. I'm sorry. No, it's not. It's combinational. The control unit is combinational. It has no state, has no memory. So it's going to use this register as a way to make itself remember that in the previous cycle, it wanted to stall the next instruction. Does that make sense? Now you have to be very careful because now you have an output called stall and an input called stall, and you've got to make sure that you've got that register that breaks that path up. Because if you don't, if you forget to put that register in there, which in this class usually there's a few groups that'll do this, you'll end up with a loop, a combinational loop, right? Right? You got to make sure that there's a one cycle delay between the output and the input. Otherwise, what will happen is the control unit will say, I've got a branch, stall. And as soon as it says that, combinationally, that stall signal will convert the incoming instruction to a no-op. And then the control unit will say, oh, look, it's a no-op. We don't need to stall. And then it'll set the stall to 0, which will convert the instruction back to the branch. And then it'll say, oh, it's a branch, I have to stall. And it converts it to a stall, and then it sees, oh, it's a stall, I don't need to stall. And you end up with this infinite loop, right, that's happening within the clock cycle. It's not clocked, it's a combinational loop. So Model Sim will lock up if that happens, because what will happen in Model Sim is that it'll trigger a cascade of events. It'll trigger a cascade of circular events where something happens that triggers an event, which triggers something that triggers another event, and that happens endlessly. And for whatever reason, when you do that, we noticed that when I used to teach this class in VHDL, if you did that in VHDL, Model Sim would say iteration limit reached, 10,000 iterations bailing out. But in Verilog, it doesn't have that iteration limit for some reason, and it just locks up, it hangs. I don't know why, because it's pretty much the same idea, but I don't know, so it'll lock. And these are really hard to track down. If this happens and you have a loop in your code, there's really no way to diagnose it other than randomly commenting parts of your design out to try to narrow down where that loop is. You might say, come on, you just look for a loop. Well, no, because keep in mind, the loop might be passing through the hierarchy of your design. So sometimes it's not obvious where these loops are. So whenever this happens to me, I literally just comment out half my design and see if the loop is still there, right? And I try to do a binary search to narrow down where the loop is. Okay. So that's basically all you need to add for the control logic. Well, for the I should say the structure inside the fetch stage. There's another detail here though. There's this jump and link register and jump and link. There's a jump and link and there's a jump and link register. These instructions are also linking, meaning that they want to store the address of the fall through instruction, which they're stalling. Right? They're going to kill the fall-through instruction in terms of executing it, but they want to save its address so they can come back to it later. Right? That's the return address, right? So that means that you have to save which program counter? you want to save, so this is where it gets weird because, okay, the branch is in execute. The link address is in fetch when the branch is in execute, right? So when the branch is in execute, or I should say not the branch, sorry, the jump and link. I should say jump and link, because branches don't link. They do in ARM. ARM processor has branch and link, but RISC-V and MIPS only have jump and link. Okay, so when the jump and link is in the execute stage, we want to save PC fetch, right? Meaning the next PC, not the current, but the next PC, right? Make sense? However, that's going to happen in the write-back stage. The actual linking is happening in the write-back, which means that you're going to save the link address when the branch gets to write-back, which means that you're not actually writing the PC fetch, you're writing now the PCEX, right? Because when the jump and link is writing back, the fall-through instruction, which is of course a stall, but the address of that instruction is going to be one cycle behind it in execute, right? Which means that the value you write back to the register file is going to be PCEX. Now that's kind of that's a little weird though, because I said that anything in write-back, anything you do in write-back should happen to _WB signals, right? Not WEX, right? We added the suffix to avoid any confusion. All the write-back signals have _WB, but what I'm telling you now is that you're going to write back PCEX, which violates that rule. Well, the reason is because PCEX is the address of the instruction that is back in execute when the jump and link is in write back, right? Does that make sense? So what you're doing there is you're going to, sorry, I should bring up the slide. Yeah, right here. See? So what I've done here is this is the reg select mux. This is what decides what you write back to the register file. Remember, option 0 is the LUI, option 1 is the, no, sorry, option 0 is the switch IO, you know, the input thing, right? Option 1 is the load up or immediate thing. Option 2 is the normal ALU result, right? And we've added an option 3, which is the program counter. EX though, which again is weird because normally stuff in write back has the _WB, but this, we deliberately want to grab something from the execute stage to use in the write back stage because we're referring to the link instruction, which is one cycle behind. Does that make sense? And then, of course, the program counter is only 12 bits, and we have to convert it to 32 bits, so that's why we add 20 zeros there. Zero padded, right? Any questions? Yes?
So, I'm trying to understand. Are you suggesting we just stall one cycle after every branch?
No. If the branch is not taken, you don't have to stall. So what that really means is that the stall signal is actually kind of linked to the program counter source. So the program counter source is determining where you go next. So under normal circumstances with no change of control, PC source is 0, right? And if PC source is 1, 2, or 3, that means you're taking a branch or a jump, which means that the stall signal is essentially just saying, if PC source isn't 0, then stall, right? I mean, that's basically what's going on, although I have it shown as a separate output, and I always make it its own output. But this stall is literally just saying, as long as PC source is 0, that means just there's no stall. If you set PC source to anything other than 0, then there's going to be a corresponding stall that's going to come with that, because it means that it's a... But if the branch is not taken, then the PC source will be 0, right? So you're not going to stall if you have a branch instruction that's not taken, right? Yes?
Conditional branches, because that's not resolved with just the 0.
That's right. Yep, I'll get to that. Yeah, I'm gonna get to that. So yeah, let me talk about that now. So how do you resolve branches then? How do you decide whether, if you have a branch, how do you know if it's taken? So if you guys, I don't know if you remember this, but in 212, in the Hennessy and Patterson book, they have an example CPU design, and the only branch they had is branch if equal, I think, right? Branch if equal, branch if not equal. And thus, they use the 0 signal to determine whether the branch should be resolved. Why? Because when they get a branch, because there's only 2 branches, branch if equal, branch if not equal, both of those branches take 2 inputs, right? So you take those 2 inputs, you subtract them, and if the result is 0, then they're equal, right? And so you use the 0 flag from the ALU to determine that. So that's all they do. But if you have branch less than, what do we have? Branch less than unsigned, branch greater than equal unsigned. So if you have these other branch instructions, then instead of subtracting, you can use the set less than ALU op. And then instead of using the 0 output from your ALU, you can use the R output, right? So now, luckily, there's no branch if greater than, because then we'd be in big trouble. Because branch if greater than would be impossible, wouldn't it? Because branch if greater than is going to give the ALU 2 inputs, A and B, and it wants to know if A is greater than B, but we don't have an operation for that. There's no way to tell if A is greater than B. But A less than B, you use the set less than. A greater than or equal to B, you still use the set less than, you just complement it, right?
So we're not changing ALU, we're just using the R output of it.
Right. Exactly. You don't have to change any. Yeah, you just. The key is to set the right ALU op, depending on which branch instruction you're doing. And inside your control unit, you have to use a different input to determine whether the branch is taken, depending on the branch instruction. So what that means is your control unit will have to have a nested if statement, right? You'll have to have an if statement inside your if statement for the branch that will add an additional layer of checking, right? I mean, you don't have to do it that way. That's the easiest way, I think, to do it. You could probably flatten. You have to be careful, though. I would use a nested if statement for branch resolution. Unless you want to create an external branch resolution unit, which you could do that too. You could do it that way. Yeah, that's fine. That's what Hennessy and Patterson did in their book. They had a little AND gate that resolved the branches. But because we have more branch instructions than they did, I think it's easier to create a monolithic control unit, put all the control into one unit, including branch resolution. Did you have a question?
Yeah, well, I guess I'm kind of answering, but I guess the RISC-V doesn't, the branch greater, or like all the other branches aren't pseudo instructions.
No, they are. Yeah, I think you can do branch of greater than, and what it'll do is it'll treat it like a pseudo instruction, and it'll swap the 2 registers and then treat it as a less than. So if you do branch greater than, that's equivalent to branch less than with the operands swapped, right? So the assembler could take care of that. Does it make sense? I think that's how it works. I don't know if I ever tried that, but I'm pretty sure that's how it works. Of course, you could do it in hardware too. If you added another mux, like if you added mux inputs to the ALU to allow A and B to be swapped, then you could handle that in hardware, but then you'd add extra delay because you'd have more inputs on those muxes. There'd be a cost associated with that. And the RISC-V guys are trying to make this thing as fast as possible. So they don't, that's not the approach they want to take. Okay, any questions about that? So just to summarize, I think I have a summary here, right? I don't. Okay. Yeah, so I do. Changes, yeah, here we go. This is my summary slide. These are all the things you need to change to your lab 3. So you need to add the branch address, JAL address, JALer address. So I gave you the code for calculating those, but then you have to add those as possible next state values for PC fetch, right? Meaning that you have to add a mux to your fetch stage, and you have to add that PC source as the control for that thing. add PC source EX to the control unit, add stall fetch as an output of the control unit, and stall EX as an input to the control unit. And you have to add PCEX as a fourth option for the for the reg dest mux. Okay, which I showed that in the diagrams. And then inside your control unit, you're going to start your control unit with an if statement at the very beginning that says, if stall EX is asserted, then do nothing. Else, and then everything that you've got in your control unit now will be in the else, right? Now, unfortunately, that's going to make debugging a little tricky, though, because what that means is, here's your test program. This is a test program I came up with for this lab. So how do you know if the program's working is the question. How are you going to test this? What is your criteria for a correctly working CPU when you have branch instructions? Well, remember in the old test program, our criteria was whether the registers were written correctly, like if the program resulted in the correct sequence of register writes. In this program, it's the program counter, it's the sequence of program counters, right? The problem, though, is that it really gets tricky because you have to remember that the program counter has a delayed reaction to every branch or jump, right? So what will happen is that you look at here's the program. Now remember, the program counter is a word address, so it's ticking up by 1. So each instruction has each consecutive, or each instruction increments the program counter by 1. So you're going to fetch program counter 0, 1, 2. Okay, that's fine. But then instruction 2 is the branch if equal, and it's comparing -1 and 2 that are in registers 4 and 5. Obviously, those are not equal, so that branch is not taken. So the next fetch is going to be 3. 3 checks to see if register 4 and 5 are not equal, which is true, they're not equal, at which point we're going to branch to target 3, and target 3 is 8. Right? Now the problem, though, is that there's a delay because we're actually going to fetch instruction 4 before we jump to 8. So the sequence is 0, 1, 2, 3, 4, but that 4 is a stall, but it's still going to get fetched. So you're still going to see the program counter is going to get 4, but then after 4, it's going to go to 8. So what happened really is that I executed 0, 1, 2, 3, and then I go to 8, but that 4 is still going to be in the sequence, the fetch sequence, right? And then 8 is going to be a jump and link. But again, that's going to have a stall. So we're going to jump to target 1, which is 4, but there's a delay. So after 8, we're going to fetch 9, that's our stall, and then we're going to go to 4, which is our intended destination of instruction 8, right? Then 4 is a BLT. We want to know if -1 is less than 2, which of course it is, right? So we're going to go to target 4, which is 9. But again, there's a delay. We're going to get 5 and then go to 9. And then at 9, we're going to jump and link register to whatever's in X1. Okay, now this is where things get a little weird. What's in X1? I never initialized X1. What is X1? What's in X1? Well, X1 would have been a link address, right? From where? From 8. Right? So when I executed this instruction at 8, because 8 wasn't a stall, right? I would have linked 9 in register X1. So later, when I jump and link register to X1, I have instruction 9 executes, instruction 10 executes, but it's a stall, and then I go back to 9 again, right? Because 9 was in register X1.
When PC5 is the jump and link target 5, is that a format that does not require a register?
No, it just 5 never got executed because it was a stall. We never actually execute 5.
The way you have it coded, there is no register to put the...
Oh, yeah, that's a good question. That's a good question. In RISC-V, there is actually a register. but it defaults to register 1 is a default. You can put, that's a great question. So in the J-type, yeah, so this is the J-type instruction that JAL uses. There is a register RD, and you can put it in, but if you don't put it in, it uses 1. Yeah, in MIPS it was 30, I don't know if you guys remember, but in MIPS 31 was the link, the default link register, but in RISC-V they changed it to 1. Again, I don't know why, but it causes confusion if you know both, instruction sets. Yeah, I just didn't put it in. I don't know why I didn't put it in. I think I didn't put it in because I adapted this from, originally this was a MIPS program. When we used to teach the class in MIPS, and then when we went to RISC-V, I changed it to RISC-V, but I didn't, because in MIPS, the jump and link didn't have a register. The jump and link register allowed you to specify the link address in MIPS, but anyway, but it still works.
Because the compiler took care of that anyway.
Yeah.
Little full instruction in it.
But this works. You can put this in RARs. This is a tested program. You can assemble this. But yeah, the jump and link will, but it doesn't matter because actually register 5 never gets executed anyway in this program. Okay, so anyway, the point of this is that in order to test this, you have to follow the PC fetch sequence, which is a trace of what instructions get executed. However, you have to incorporate, every time you have a branch or jump, branch that's taken or a jump, there's that stall. So it makes it really confusing, which is why I gave you the fetch sequence for this. So you can just use mine for testing. Now, if you read the lab sheet, I'm going to update the lab sheet. I noticed today, I posted the lab sheet on Dropbox, and I remembered that the lab sheet goes into a lot of detail about your test bench. It talks about how you should have a test suite where you test each instruction. I always tell students that they can use the test program as a way to test their CPUs as long as they have a methodology for testing it. So what my methodology is looking at the program counter, right? And tracking the program counter as it moves through the program. If that's what you're doing, that's good enough for me. Of course, you also have the option of having your own test suite where, for example, you write a test bench that monitors the program counter automatically, right? Or you could do unit testing of individual instructions or small groups of instructions as opposed to putting this whole test program in. That's up to you. Yes?
So just to clarify, it doesn't really matter how we test it as long as we can or justify it to when we're done.
Exactly. Yeah, that's what the demo is for. Yeah, you just explain how you test it. So we're usually pretty vague about the testing, although obviously my position is you should be able to use this program to test it because this program tests every instruction. The problem though is it doesn't test it tests all the branch instructions, but it doesn't test both outcomes of all branch. So in that sense, it's not really a good test. But if your CPU gets through this, then I'm happy with that. Right? Now this is one test program. The other test program is now we want to go back and have you run your square root code. So now the square root code is even a worse test because you're not necessarily even going to use all the instructions at least once, but it allows you to actually build a tangible calculator, right? So the idea is that we want you to take your square root code and take the switch values, calculate the square root, and then use the binary to base 10 conversion to print out the result to the hex displays. Make sense? Now this is a little weird though because the switches are allowing you to specify an integer, a whole number, right? But the square root of a whole number is most likely going to be a fractional number, right? So the problem is we're going to put a whole number in, calculate the square root, and we want it to somehow show us the fractional result of that. So the way to do it is to treat the decimal hex displays as a fixed point where the first 3 digits are whole digits. And when I say digits, I really mean digits, base 10 digits. And the other 5 are fractional, right? Why? Because If you take all the switches and push them up, that's going to give you an input value of 262,143, I believe. And the square root of that is like 511.9999999, right? So the range of the output, the maximum output is going to be just under 512, right? Which means we only need 3 whole numbers followed by 5 fractional numbers. Does that make sense? So how do we do fixed point in base 10? How does that work? Easy. You just do everything in fixed point binary. And when you're done, you multiply the binary fixed point value by 100,000. Right? So you take whatever, so for example, if I put 2 in, the answer of square root of 2 is 1.414 something, right? You take that number and you multiply it by 100,000, which will basically just shift it to the left in base 10, and then you do your binary base 10 conversion. So what you end up with is, a working system where you flip your switches, the switches are read in by your CPU, you run code to calculate the square root, then you convert that to base 10 and you output it to the hex displays, and you'll actually get a square root. Now it'll have a little error because the format we're going to use is the format used. What format did you guys use for lab 1? It was 14 fractional bits, right? So 14 fractional bits has an accuracy of 2 to the negative 14th power, which is 1 over 16,000, right? But on the board, the smallest number is 1/100,000th, right? So 1 over 16,000 is a bigger number than 1 over 100,000, which means that the hex displays have more precision than your code's going to have. So your hex displays will be off by as much as 6 or so in the least significant digit or so. But it'll be pretty close, right? But you'll have a little bit of error because the hex displays actually have more expressibility than your binary values in 32-bit. Of course, you could always do a 64-bit version and fix that, but we just want to do a 32-bit version. Okay? Make sense? Okay. So I described that here. Yeah, so it's in the slide. Okay. Any questions about that? Okay, so now remember, one other thing I want to remind you of is that the grades for this class, if you look at the syllabus, the grades are weighted where they add up to 117.5%, okay? And the reason for that is because if you choose to, if you feel overwhelmed by this lab, I mean, you have a month to do it, and like I said, if you have lab 3 working, it's not really that much more code to add, although the control logic can get tricky and confusing. But if you don't think you can handle this lab, you can opt out of the lab as long as you feel pretty strongly about doing well on the final exam, right? On the other hand, if you prefer to do hands-on work, you can do really well in this lab and then not take the final exam, right? That's up to you. That gives you the flexibility. Now, what's on the final exam? From this point forward, we're going to cover some conceptual stuff. So the next lecture is going to be on sequential logic, which is state machine design, basically, finite state machines. That's something that you need if you're going to design a bus protocol. Like any kind of bus protocol, you have to request the bus, and then it grants it, and then you have to send the address, and then it gives you an acknowledgement, and then you got to send the data. All of that requires states. You have to go through these. The circuit has to be in a certain state. And for those of you that were here last week, I did an example for the exam from chipdev.io, which used a state machine. So I'm going to go over that. Then the lecture after that is the one. My favorite lecture is on timing analysis. How do you calculate the speed of a digital circuit? How do you calculate the clock rate? So we're going to talk about setup time and hold time and timing closure. That's what the CAD tools are doing to guarantee that your circuit will work at the clock rate that you want, right? So that's a lecture. Then we're going to do digital building blocks, which is where we're going to look at adder architectures, multiplier architectures, comparators, things like that. So kind of basic building blocks for digital logic design. divider architecture. We'll talk about why we don't have a divider in this class, why that's so expensive. And then the final lecture will be CMOS logic. I'm going to go into some transistor level logics because, unfortunately, we don't require you guys to take a VLSI design course, which is like the design for manufacturing ASIC design, like low-level design, semiconductor design. And so I used to teach that class though, so I have basically my introductory lecture for that class I've pulled into this class. So you get an idea of what it takes to design an ASIC as opposed to using an FPGA. I think that's good background to have. So we'll talk about some semiconductor theory and then CMOS, how you use transistors to build logic gates and how you calculate the timing for those, the performance of those circuits. So that's the rest of the class, just to give you an idea. So all that will be covered on the final. So you can, think about, whether you want to focus more on the project or the conceptual material. And then we'll have some quizzes too. The quizzes you can't opt out of, but quizzes are easy. Get a whole week to take them.
Is the final comprehensive covering?
Yeah, it's comprehensive, but I'm going to focus a lot on the conceptual stuff. But it will be comprehensive, yeah. But yeah, like I said, most of the questions will come from the new material. Okay. Any questions?
About Lab 5?
Oh, if you're a grad student, yes, that's a good, thank you. If you're taking the class for graduate or honors credit, there is a Lab 5, and I can talk to you about that individually. So Lab 5 is, if you're doing Lab 5, that builds on Lab 4. So you have to do Lab 4. Of course, you can opt out of Lab 5, though. So basically, if you're a grad student, you can do Lab 4 and the final and not do Lab 5, right? In which case, you can take advantage of the opt-out, but you can't opt out of Lab 4 and 5, right? Anyway, but Lab 5 is where we're going to try to do a superscaler, extend the CPU to execute 2 instructions per clock, right? So we're going to add another ALU, we're going to add more ports to the register file, and we're going to add another control unit so we can double up, right? Which is principally how you get more performance out of CPUs is you get more instruction level parallelism, you execute more instructions in parallel, right? But that requires some additional things in the assembler too that we have to modify. Okay, but I'll talk to you guys individually about that. Okay, so if you're a grad student and you're in a group with another grad student, you can both work on it. If you're a grad student and you're with an undergrad student, then you'll have to do it yourself, right? And the syllabus has all the details of how the weights reflect that. Okay, any questions? Okay, all right, sounds good. Then we'll see you next week.